First and foremost, I'd like to say that these sessions starting today are a completely different perspective of what we usually expect from a conference or a training on resilience. In 2012, I decided to start a research based on what I've learned until then about risk management and business continuity. This idea became into a long lasting commitment, resulting in several math based research papers and two books with the findings that I will present throughout these sessions. The title of this series is because most of my research on resilience is based on a branch of mathematics called mathematical analysis. Today, we will see what we are missing when using some of the most popular risk assessment tools, making of many times strategic decisions, an action that exposes the organization to more serious risks under a false sense of security. What are we going to see today? A new risk map different from the traditional heat map, and why changing a so familiar and widely used tool in risk assessment? Because the heat map inherently biases the risk assessment while forcing the organizational risk perception. And finally, how to use it. Once defined, the organizational risk map, the assessment is carried out exactly as with the usual risk map by just providing a probability value and an estimated impact. Let's see how the typical heat map is inherently biased, forcing the organizations to unwillingly adopt a quite similar or the same risk perception. This is how we lose an important dimension when working with a heat map. It is like projecting a three-dimensional object on a flat surface. This is turning a sphere into a circle. What we want to do is to gain a more powerful tool, turning a two-dimensional into a three-dimensional risk analysis. Suppose that we live in a plane and we have two freedom degrees, which combined makes us reach any destination in that flat world, no matter how curled or angled the path be. But when we add a third freedom degree or a third dimension, we can do the same. This is going everywhere we want as we used to do in a flat world, but this time flying in a 3D space. Here we have a traditional heat map, which along with a very typical formula of A times probability plus B times impact are possibly the most popular risk assessment tools used, at least for operational risk. And we will talk probably later about this formula. However, I want we to take into account that the heat map is not only a representation tool. I mean, when the heat map is fed with dots representing the organizational risks, it reflects the risk perception or the risk profile of that organization. In this example, if this ant travels along the dashed line, the risk level holds yellow. This means a zero relevant change in risk. This way, we are assuming that there is a certain balance between probability and impact, meaning that a zero probability event with an impact of 3 is the same risk as a risk of zero impact with probability of 50%. And there are two serious consequences of this behavior of the risk map. Looking at the red region, if we take a hurricane of 5 miles per hour, which is just a soft wind, with 100 probability of occurrence, represents the same risk of a category 5 hurricane with zero or almost zero probability of occurrence. And probably you notice that this scenario is quite similar to a pandemic. And we know the effects of a pandemic, even though that event was supposed to be a close to zero probability event. I don't know what you think about, but it seems to me that this conception is quite arguably. Now, a second consequence is that by using this heat map, we are assuming that every organization with a map like this or a similar map has the same risk perception, and that will lead to the same risk profile without any possibilities of escaping from a biased perspective imposed, this time by the assessment tool itself. On the other hand, this complicated what you see on the right is the mathematical expression for the red region. We are representing here mathematically just the red region. And this is just to show how difficult it may be to describe a complete heat map mathematically. And let me tell you that this is the easiest part because working with it is absolutely impractical, mathematically speaking. Now, taking our heat map and put it down on the floor, imagine that we have plotted these four risks in our heat map, three orange risks and one red risk. each of those. I mean, these on the orange region and this single red risk in the red region. Now imagine that the orange risk plotted on the plane are only the projected shadow of three orange risks some height above the heat map. This height corresponds to a risk level, exactly a risk level, which means that every risk with the same value will be on the same orange plane at that specific level. Likewise, a higher risk will be the result of a greater probability, I mean, pointed out of the screen, and a greater impact towards the right in some proportion. This is exactly what it represents. What is represented here, just moving towards the right a little bit, it corresponds just to a real higher level or layer in our three-dimensional risk map. We can see that the traditional heat map is nothing else but the shadow of a three-dimensional risk representation, which depending on the proportion or combination of probability and impact, a risk will be on a higher risk level or in a lower one. Now, there is something important to highlight here. A subtle shift of a risk impact in the proximity of the neighbor red region makes the risk to get onto the next level. This is no matter whether we slide the orange, one of these orange risks along the whole orange plane with important changes in probability and impact, but suddenly an insignificant change in the border with the next level make the risk jump from a mid-high level to a critical level. And this is just an intuition of what I'll explain later. Here, what we can do is just replace the typical heat map by a three-dimensional risk map in this fashion. Obviously, this is not definitive, but it's an intuition that's going to help us for what's coming next. Now, we know the risk level is the result of our relationship between probability and impact. And remember that for any non-deterministic event, the probability is completely independent from the impact, except in the heat map. In mathematics, a variable depending on two independent variables is formally defined as a surface in a three-dimensional space. In our case, risk level depends on probability and impact, which are independent from each other. Okay, this grid represents a typical heat map. But let me remove the lines that define this grid just to show you how an organization, a typical organization, looks at its risks. This is the risk profile. This organization believes that every probability increment corresponds a risk level increment. This is a greater probability comes with a higher point in the surface, and the same happens with the impact. Exactly the same happens with the impact. But with a three-dimensional risk map, every organization may and should have its own risk profile. So let me show you this other organization's risk profile, just to see how it looks like. This is another organization, a different risk profile. So this organization, for example, this organization believes that if a risk has zero impact, no matter how much the probability increases, the risk level will be zero, which is represented by the surface attached to the probability axis. In general, every organization is supposed to perceive its risks in a different manner. So risk profile is like a fingerprint. There should be a surface for every organization that once created just wait to be filled with each organization's risk constellation like this. Thank you very much for joining. I hope you have enjoyed this session, and I hope to see you in the next video.